Welcome AP Mechanics students. Today's review video is on simple harmonic motion. Now in the AP curriculum, simple harmonic motion is usually lumped in with gravitation in one unit. But what I've done is I've split that one unit into actually two review videos because I felt that it was going to be too much. The ideas and the concepts are not really all that related anyway, so that's why I split this video into just simple harmonic motion. That being said, here's a list of the topics we're going to be talking about today. There's the kinematics of simple harmonic motion. Remember, kinematics is just a fancy word for a mathematical description of the motion of an object. By mathematical, we're talking about formulas and graphs and functions for the position of something, the x-coordinate, the velocity, the v, and the third, the acceleration, just formulas for not the y. Then we're going to move on to simple harmonic motion and Newton's laws, how Newton's laws come into play in simple harmonic motion, then how energy, we can analyze simple harmonic motion in terms of energy. Then we're going to look at one application, something oscillating on a vertical spring. And then the last thing we're going to do is we're going to be deriving formulas for the period of simple harmonic oscillators, notably the mass on a spring and the pendulum. So that's what's coming. You don't have to jot this down because it's coming up in the notes. So let's begin. Here we are, the kinematics. I just want to remind you that a simple harmonic oscillator is something that goes back and forth, a real smooth, clean vibration. And what we do is we label the very middle of its motion as x equals 0. That's the coordinate 0. When it moves to the right of that, we label that as positive x. And when it moves to the left of that point in the middle, we call that negative x. So this, we're going to see later, is most commonly caused by something oscillating on a spring. So at one point the spring gets stretched. Well, this is where it's relaxed. Then the spring gets stretched, and then it gets compressed. So you've got a spring here, and you're sort of oscillating on that spring. The first equation is for the x-coordinate. By the way, here's a graph of its motion. So if we begin the object here, we pull this object by stretching the spring, and then when we start a timer, we let the object go. It'll go like this, oscillating back and forth, starting at positive x, going to negative x, and back to positive. That is a cosine graph that it would trace out. It would begin at x equals plus a. That's the point of furthest motion to the right in the positive direction. We call that the amplitude. And then this is negative amplitude. So amplitude is not this distance. It's from the middle out, okay? So the object begins at x equals plus a, then it races back to the origin, so that's where it came back here. Then it goes into negative displacement, so the graph goes negative, and then it goes back to the zero, or the origin of our x-axis, and then it overshoots and goes like that to this point, to positive x, and then it repeats that. So this graph keeps going. It's a cosine graph that continues on. So mathematically, we could write a formula for the x-coordinate as x equals a cos theta. Remember, cos theta oscillates between positive 1 and negative 1. So we're oscillating between a times positive 1 and a times negative 1. There's the x, or the this axis of our graph. Now, you could also have a sine function. That would be an oscillator that starts in the middle and then gets a momentary whack out in the positive of v0, an instantaneous burst of velocity. So it starts at the origin and goes in the positive direction, and it traces out a sine graph. Okay, so it'll go like that. But I didn't focus in on that one. Strictly speaking, an oscillator can begin at other points, and so we can have other kinds of graphs. What we would have in such a case is a term over here plus some kind of phase. But that, as far as I know, is not in the curriculum. The oscillators either begin here or begin there. So if they begin here, then the graph is a cosine graph. If they begin here at x equals 0, then they're a sine graph. Okay, so those are the two possibilities. This omega term is 2 pi divided by the period of oscillation. So let's suppose this thing takes 4.4 seconds to oscillate back and forth. So that means I start the stopwatch when I let it go, and it goes all the way here and back, and we stop the stopwatch. That time is what we call the period, okay, the time for one oscillation. So we put that in under 2 pi, and we put that all in for omega. And I want to just take a few minutes to explain how this function works. It's very logical mathematically. So here's, you don't have to write this down, by the way. I'm just going to talk about this so you kind of more for understanding. So here's this expression with the omega plugged in of 4.4 with period of 4.4 seconds. So when the timer begins at time 0, this whole thing in the parentheses is 0 times all that. So we have 0. Cosine of 0 is 1. So the graph starts at a times positive 1. It starts here. Then the time keeps running, so the term inside the cosine function is no longer 0. A little bit later, let's suppose at time 1.1 seconds, we want to know where the oscillator is. So if we plug in 1.1 seconds, what we have is 1.1 divided by 4.4, which is 1/4. Okay? So then we have 2 pi divided by 4, which then becomes just pi over 2. 2 pi over 4 is pi over 2. So then at that moment, at the 1.1 second mark, our cosine expression, cosine of pi over 2, is 0. Okay? So the x-coordinate at 1.1 seconds is 0. The time keeps running though. Let's suppose a little bit later, the time is now 2.2 seconds on our stopwatch. What's in this parentheses then is 2.2 divided by 4.4, which is 1/2. So we got 2 pi divided by 2, which just gives us, inside the parentheses, pi. So what do we have for an x-coordinate? Cosine of pi is -1. So we have -1 times a, so that means x is -a at 2.2 seconds. -a at 2.2 seconds. So the cosine graph is now here. What about if we go on, the time runs on, not to 2.2, but 3.3, okay? Then what we have is 3.3 over 4.4, which is 3/4. So we have 2 pi times 3 over 4, which is 6 pi over 4, or 3 pi over 2. That's what we have at 3.3 seconds. This is all 3 pi over 2. What is the cosine of 3 pi over 2? Well, that's also 0. So the x-coordinate at 3.3 seconds, right here, is 0. And then the timer keeps running, and instead of 3.3 now, the timer reaches 4.4 seconds, the same as the period of oscillation. So what we have is 4.4 over 4.4, which is 1, leaving us just 2 pi in the parentheses term. So our cosine function is 2 pi, which is, the cosine of 2 pi is 1 again. So we have 1 times a, so at 4.4 seconds, we're back to x equals a. And then this continues on and on. In other words, at 8.8 seconds, we've got 8.8 over 4.4, which is 2 times 2 pi, or 4 pi. We are here in our cosine graph. We've gone through another cycle. Another 4.4 seconds gets us to 13.2 seconds. 13.2 over 4.4 is 3. 3 times 2 pi is 6 pi. So now we're through another cosine graph. And that keeps going indefinitely. So that's the logic behind this equation. Understanding that may help in the problems, in some of the problems in the future. But let's move on with the material. So, what is the velocity? Well, we could think about the velocity physically in our understanding of how things move. So, for example, here, when we let the thing go at time 0, the velocity is 0 because it's in our hand and we just let the thing go. Then the thing starts going in the leftward direction in negative velocity. And then right here, when we're in the middle, x equals 0, we're moving backwards with the most negative velocity. We're going this way. And then what happens is the x coordinate goes more into the negative, is the thing is slowing down and reaches 0 velocity here. So when we reach our maximum x negative coordinate, we are at 0 velocity again. Now it starts racing in the positive direction, positive velocity, and when it gets back to the middle here, we are moving forward in the greatest possible velocity. Then it starts moving forward and slowing down and gets to 0. So we could generate that graph just from physical considerations and our understanding of motion. Or we could use the definition of velocity as the derivative of x with respect to time. If you take the derivative of cosine, you get negative sine, and the a constant stays there. But we need to use the chain rule, so if we just had cosine of t, the derivative would be negative sine of t. But now we have to multiply by the derivative of what's inside here. The derivative of omega t is omega, so that gives us the extra omega here. So this is the derivative, negative a omega, and look, that's a negative sine graph. And then the velocity oscillates between positive a omega and negative a omega, because that sign goes between 1 and negative 1. So we oscillate, those are our maximum velocity and maximum negative velocity, maximum positive velocity. Okay? The acceleration we can get by taking the second derivative, in other words, take the derivative of the velocity function. The derivative of sine is cosine, the negative a remains, but we have another omega because we've got to use the chain rule, so we multiply what's in front by the derivative of this, which is omega, giving us omega times omega, omega squared. So this is actually the maximum acceleration, positive or negative, as cos is oscillating between 1 and negative 1. So there are the maximum accelerations, positive, negative. And I've created vertical lines for reference so you could see. So also remember F equals negative kx for a spring, which I'll talk about later. So that's the acceleration is negative of the x coordinate. Okay, so it's a negative cosine. If this is positive, F equals negative kx makes a negative cosine graph. So another way to generate that graph. So this is kinematics, just describing the motion of an oscillator. All right, here are a bunch of formulas too that I wrote down. I'm going to later prove these two, derive them. But this is the period of oscillation for a mass on a spring. Anything that's oscillating on a spring with F equals minus kx. Why the minus sign? If I pull in the positive x direction, the force is in the backwards direction. Positive x, negative force. If I go in the negative x direction, the force is in the positive direction. Negative x, positive force. So there's a minus sign there. That's critical in simple harmonic motion. Include that minus sign in a lot of problems. Okay, so notice things that are missing. No amplitude here. Okay, so whether something is oscillating on a spring like this or oscillating like this, counterintuitive that the period is the same, independent of the amplitude. All that it depends on is the mass, more mass, longer period, more spring constant, less period. Remember, spring constant is the tightness of the spring, how rigid it is. So if we've got a real tight spring, it causes a fast vibration of small time. Pendulums. So we could put a mass on the end of a string like this and let it swing back and forth. The period of oscillation, 2 pi L over G, square root. G is 9.8 on Earth. L is the length of the string of the pendulum. So like this, with a ball of mass down here. So that's L. Notice again, no amplitude and no mass of the pendulum. If I put a lead ball down here, or a steel ball, or a wooden ball, and this is a light string with very little mass, negligible mass, period's all the same. A little aside though, later we're going to see that the amplitude needs to stay relatively small, like maybe less than 10 degrees, because we generate this formula through approximation, and we'll see that later. This is for a torsional pendulum. So we can take an object and we can make it oscillate like a spring like this, and we can make it oscillating like this. But if we look at this from a top view and we've got a spring like this, I could twist that spring and then it'll oscillate like this. Okay? So a twisting oscillation. Period, the radical term, this is the spring constant for twisting, kappa. Okay? Negative kappa theta is like F equals negative kx. The greater the theta, the more torque you get back on the spring. And so this constant of proportionality is what goes into that. Tighter spring has a greater kappa. And this is the rotational inertia. And this also, from the rotational motion topic, which we reviewed in the last video, you can have what's called a physical pendulum. So like this pencil is, if I drilled a hole here, it has mass all throughout, not just at the bottom. This is a physical pendulum. So the period is given by that. This would be the inertia at the axle. Okay, so here it is, some kinematics. All right, we're going to move on to the second piece of information for today, simple harmonic motion and Newton's laws. So the first thing is that if the motion is spring-driven, let's suppose it's oscillating between these two lines here, the object. This is x equals 0, this is x equals plus a, this is x equals minus a. The spring force, as I mentioned, is minus kx, because when you go in the positive x direction, the spring force is to the negative direction. When you go to the negative, the spring force is positive. So here are the force diagrams. Notice we got gravity in all cases as this is going back and forth, and normal force of the surface it's being supported on, balancing out gravity at all points. Now, when it moves to the left of the equilibrium, the force is to the right, and that's true whether the object's moving this way or it's moving that way. As it's coming this way, the force in the backwards direction is to decelerate the object, to slow it down. So the force is that way, slowing it down. When it reverses direction, the force is still in the same direction, but this time it's accelerating it, speeding it up. Losing speed this way, gaining speed that way, because the force is always to the right, the acceleration is always to the right. Right in the middle, the spring is not exerting any force, so there's zero acceleration in the middle, net force 0. And then when it overshoots this way, as it's moving this way, the spring is pushing this way, so it's decelerating, then it reverses direction, so its velocity is this way, and the force is that way, so it's accelerating. So whether it's going left or right, if it's to the right of equilibrium, the force is to the left. And whether it's moving forward, backwards, the force is always to the right in that part of the motion. So sometimes you have to draw force diagrams. Keep that in mind. Students sometimes flip the force around when it's accelerating or decelerating. Then we use the expression Newton's second law, ma equals F net. That's the convenient way that I find in most this SHM stuff. So ma, keep in mind that's the second derivative of x with respect to time, and the net force is just the spring force, negative kx, and that'll come into play later. Another thing I want to point out is sometimes the simple harmonic motion is it's not spring driven, it's actually driven by friction. And so let me show you an example of that. So here I have a block on a piece of paper, and if I move the paper according to, so this is in simple harmonic motion, the paper, that's driving the block in simple harmonic motion. And what's driving that block? No spring, friction, okay, because it's rooted to the piece of paper. Okay, so in this diagram, these become force of friction. Okay, so same force diagrams except no Fs but Fs. So the first example that I want to talk about is a shake table. That's what I was just showing you now. Now some things that I want to point out is that the shake table has a limit to how fast you could do this, because see, now we get slipping. So I cannot, there are conditions at which simple harmonic motion is no longer going to happen. What are those conditions? Well, first thing, using Newton's second law, ma max comes from the force of friction max. Now, the maximum acceleration I figured out here was a omega squared. And the maximum friction is mu f normal, plugging in the static coefficient of friction. Normal force is mg, and then the omega term is 2 pi over the period, which is actually, maybe I'll add it here, you could add it also, 2 pi times the frequency, because frequency and period are reciprocals of each other. A reminder, frequency is how many vibrations you get in 1 second. This is how long it takes one vibration to occur. So I plug in 2 pi frequency, square that, 4 pi squared frequency squared. Notice the mass drops out, and then I get to here. And what I see is that based on a certain frictional coefficient, a couple of surfaces, wood and paper have a certain coefficient of friction. So this side is fixed depending on what the materials are made of. I'm limited in terms of amplitude. If the amplitude gets too big, this is a fixed number. I can exceed this side of the equation. This equation is no longer valid. So slipping occurs if the amplitude gets too big, or the frequency gets too big, or both. I could show you that. So here's a small amplitude, right? And then I'm going to increase the amplitude. Oops, well, so let me do a little bigger frequency. So there. And you see, when I get the amplitude, I kept the rhythm about the same, but when the amplitude got too big, we had slipping occur. And this is how we'd figure out what amplitude that slipping happens at. Or if I keep the amplitude fixed, if the frequency gets too big. So here's the amplitude fixed, and then let me go faster and faster. And now you see slipping because the frequency got too large without increasing the amplitude. So both things are limited by friction. Another possibility with a friction-driven oscillator is with stacked blocks. So maybe I've got, well, this is, if I do it this way, you can't see it that well. But yeah, so let's do it this way. So let's suppose we're looking at this side view, right? And these are oscillating like this. That's what I'm showing here. So this is oscillated, the bottom mass, by a spring. And the top block is moving along with it by the friction between the two surfaces. The top block limits how much acceleration the system can achieve, because again, the top block, friction is limited. It's not limitless. It comes from UF normal. So the top block, the MA max, is going to be equal to the maximum force of friction that we can attain. Maybe I'll put max here. Okay, so this is M top, A max, and then of course the friction is mu F normal on the top block. You see the top block's mass drops out, and the maximum acceleration the top block can sustain is mu static times 9.8. Okay. Now we can ask, well, how much oscillation can the system undergo without the top block exceeding that acceleration? So now for the system we do ma equals F net, but the total mass of the system times its acceleration is the net force on the system coming from the spring, kx. Okay. And I have to use both masses because the spring is going to accelerate both of these together while they're not slipping. And I take that acceleration that I got from the previous analysis from the top block, plug it in here, two masses, and I could solve for the amplitude maximum. I give it a small amplitude on the spring, everything's okay. Bigger amplitude, everything's okay. Too big, and then this starts slipping past, and then we don't have the blocks sticking together. This is how you calculate where the slipping, or when the slipping occurs. All right, so it's simple harmonic motion and Newton's laws. All right, let's move on. See how that looks. Pretty good. Okay, so simple harmonic motion and energy. So we have this object oscillating between x equals minus a and plus a, with x equals 0 in the middle. What happens is when we move this way, we're stretching the spring out. This is where the spring is relaxed. So we pull this way, the spring gets stretched out, and so we have spring potential energy when we're holding it here ready to release it. Once we release it, the spring energy decreases, and so we pick up kinetic energy. Somewhere in the middle, we've got a combination of the two. As the U is going down, K is going up, but adding them together is equal to what we had originally. When we get back to the middle, there's no more spring energy, so we have all kinetic energy. Then we slow down on our way out. We're losing kinetic energy and gaining spring energy. And then when we get here, we have only spring energy again. And this energy gets transferred back and forth. We could write that mathematically, that the maximum spring energy at the ends here is equal to the maximum kinetic energy in the middle, where there's no more spring energy, or somewhere in between, we have a combination of two kinds of energy, both the kinetic and spring energy. And so this is the expression above expanded out. 1/2 Ka squared is the 1/2 Kx squared with A plugged in for X is the maximum spring energy. This is the maximum kinetic energy, 1/2 mv squared, and this is the kinetic and spring in between. So a problem here, I'm not going to do an example in this case, but a problem would be like maybe I tell you the amplitude and I ask for the maximum speed. So you just have this part right here without this and you solve for Vmax. Or maybe I tell you the maximum speed and I say how fast is it moving when the amplitude's 10 centimeters. So I do this. I plug in, this is the unknown, and this is 0.1 meters, so I solve for V. So basically, you know, again, no details there, but that's the big idea here, the setup with energy and simple harmonic motion. Okay, so what's also in the curriculum is that you're expected to be able to figure out the energies as a function of time, because these are as a function of velocity and the x-coordinate. So what you would do if you were asked this on the AP to figure out the energy as a function of time is you would start with the mechanical energy expression, the spring energy and the kinetic energy, and then you would plug in A cosine. Now this is what omega is. We could figure that out from, well, it's back here. Here, if we use this and this, we could basically find that omega is radical k over m. That'll come up later. We'll see it more clearly in the derivation. So you plug in this for x and you square everything here, and then you take the derivative of x, which gives us this negative sine, chain rule, plug that all in for velocity, and you would get an expression like this. This is the total mechanical energy, which is the spring energy at the end. It's equal to the spring energy here as a function of time, cosine squared function, times 1/2 Ka squared, plus the kinetic energy, which is 1/2 Ka squared times the sine squared function. By the way, cosine squared and sine squared added together give you 1. In other words, this side is 1/2 Ka squared, just like this side. I'm going to graph these energies, the spring energy and the kinetic energy, to show you the pattern here. So let's suppose our oscillator is a cosine graph x-coordinate, so this is just to show you the oscillation. What happens is the cosine squared function at time 0, it begins at 1. Okay? Cosine of 0 is 1, square that is still 1, so our function begins right here at 1/2 Ka squared. The cosine squared function goes through 2 oscillations in 1 period. The reason why is the spring energy, we have positive spring energy in the beginning of the oscillation. We have 0. Well, let me get another. So we have 0. Then we have positive spring energy. We haven't gone through 1 cycle yet. We go back to 0. And then we go back to spring energy. So 2 cycles of spring energy in 1 oscillation. Okay. The kinetic energy, when we release this, the sine squared function at 0 is 0, kinetic energy. And then the sine squared, again, also goes through 2 oscillations, 2 cycles within 1 oscillation of the x-coordinate. And the mechanical energy straight across. This derivation is technically on the AP, but I wouldn't focus too much on it because it's not that common. In fact, I have never seen a problem with this, even though it's in the curriculum. But understanding how the energy changes, certainly this is more important, in my opinion, than all these details. Once again, I want to point out, as I've said many times, you don't need to get 100% or even 80% of the AP correct to get a 5 out of 5. So we don't want to get bogged down in details like this at the expense of something like this. This is more likely to come up on the AP than this kind of derivation. If you have limitless mental energy, go ahead and study everything. But if you feel yourself, I know myself, I know I get tired, I can't remember everything, focus on this and skip over this. Okay, that's my recommendation. Okay, let's move on. So, vertical spring oscillations. So let me explain first what I mean by vertical spring oscillation. So let's suppose this is the ceiling here, and I have a spring, and I hang a block on it or a mass, and I let this thing oscillate up and down on that spring. So what's really happening in terms of energy is now we have not only spring energy and kinetic energy, we also have gravitational energy as this thing is going up, 3 kinds of energies. But it turns out you could simplify the analysis. You could simplify the thinking by ignoring the gravitational effects. How can you do that? You could basically pretend that there's no gravitational energy, no force of gravity. First you have to, well, let me just explain the diagram. So here's the spring relaxed with no weight on it. So this is the true x equals 0 of the spring right here. Then what I do is I hang a block on here and I slowly bring it down till it's in equilibrium right here, and I let it go, and the block is at rest here because gravity and spring force are balancing each other. Gravity is down, spring force is up, and so we have an equilibrium. And the way we can expand this, we could say the gravitational force mg is equal to the spring force kx actual, the actual spring displacement right here. Once we do that, we figure out either where this new x coordinate is or the spring constant if we know what the x actual is. We ignore the fact that the spring is stretched at this point, and we label this a new x equals 0. We pretend the spring is relaxed here. That's why I put this in quotation marks. It's not the true x equals 0, but we pretend it is. If we do that, we could now ignore the force of gravity throughout the problem, as long as we never exceed the maximum amplitude here, okay? Right here. This is the maximum point. If this oscillates like this, no problem. The spring is creating a smooth oscillation. But if we try and oscillate it down here, what will happen is this will overshoot the same distance, x equals 0, and go to the point where the spring is no longer acting on this. It's like now becoming a projectile. It's flying off the spring over here. So you can't let that happen, otherwise it won't be, well, you could do it, but it won't be simple harmonic motion anymore. So you are limited in a vertical spring to keeping your amplitude small enough so that this never overshoots the place where the spring is relaxed. Any oscillation between those two maximum A's is fine. Then we could use this technique. This is now our x equals plus A, the peak of its motion, and the bottom is our x equals minus A. So now we ignore gravitational energy. We say, like we had in the previous problem, there's only spring energy here because the velocity is momentarily 0, and there's only spring energy up here because the velocity is momentarily 0. Here we say there's no spring energy because this is the x equals 0 point. All we have is kinetic energy. In between, we've got a combination of both. Okay? So hopefully that doesn't sound too confusing. It's supposed to be simpler, easier. Let's take a look at an example. I got a 2 kilogram mass, and it's stretching a spring 0.1 meter at equilibrium. So that means I let this go slowly, 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 and then when it gets to here, I let it go, and it's staying at rest here. So it's gone 0.1 meters down, and it's at rest. So this is true, okay? What the problem is asking is to determine the spring constant of the spring and the maximum speed if the mass is pushed down an additional 5 centimeters and released, and then the period. So this is 10 centimeters, so now we're going to pull it down another 5 and let it go, and it'll oscillate like this, less than here, so it's okay to use the analysis like this. That's the problem. Let's take a look at the solution. So for part A, the spring constant, what you're going to do is realize that right here, the gravity and the spring force are in equilibrium. The gravity is pulling down, the spring is pulling up. So we write that here like this. spring force is Kx, gravity is mg. I highlighted this because this is the important step, realizing that Kx is equal to mg when the thing is just hanging here at rest. Okay? And then we plug in numbers and solve for the spring constant. So again, these are just number details. Don't concentrate too much. This is the thing you want to, study what's happening right there when it's at rest. All right, now the next part here is the Vmax. If the mass is pushed down an additional 5 centimeters and release. So we push this down and let it go, and now it's oscillating like this. So the maximum kinetic energy in the middle will be equal to the maximum spring energy when we first released it. So here is everything expanded out. Again, focus on this when you study. The maximum 1/2 mv squared here is equal to 1/2 Ka squared here. So I do the algebra first. You could plug in numbers if you want, then do the algebra. I did the algebra first. Then I plug in all the data and I get 0.5 meters per second right here. I pull it down and it's going to hit here 0.5 meters per second. The last thing, the period of oscillation, was running out of a little room here, so it's a little scrunched. I use that formula, 2 pi square root of m over k, mass, spring constant, and I get 0.63 seconds. So this thing will go 0.63, 1.26, right? And on, it'll just oscillate like that. So that's a vertical spring. Ignore the gravity and just treat it as a horizontal problem with kinetic energy and spring energy interchanging. And also this little place where you find the equilibrium, the one little added twist. All right, moving on to the last thing for today. I just want to say, before I dive into the details here, like I said earlier in this video, you prioritize when you study. So if you feel like you're overwhelmed with information, I would recommend skipping this because, in my opinion, this is not as likely to be on the AP as the other parts, and because you only need about 2/3 of the test correct for 5 out of 5, even if it is on there, it may not hurt you as much as if, some of the other things are more likely to be on there. So, that being said, like I said, if you want to just stop here and say enough for today, just go ahead and start practicing. If you have enough energy, let's move on. So how do you derive this formula here? So what you do is you use Newton's laws and you create a differential equation. Remember, in the differential equations topic, a differential equation does not define a function. Like if I say x equals 1/2 at squared, that defined what x is. But if I say v equals at, that defines what the derivative of x is, because v is dx dt. So dx dt is a times t, maybe like 5t. I've defined the derivative, not what the function is. That's what Newton's second law actually is. It is actually a differential equation because acceleration is the double derivative of x. And when I do F net over m, the spring force is the only thing that creates net force if there's no friction on an oscillating mass oscillating on a spring. Minus kx is the net force over the mass. I've defined the derivative. Now what I need to do is figure out what the function is that satisfies that expression. One suitable method, believe it or not, is guessing the solution, plugging in your guess, and seeing if the equality holds. And if it does hold, you find out under what conditions it holds, and then you have the solution. Because this is oscillating back and forth, it seems logical, a good hypothesis to assume it's going to be a sine or a cosine function. Okay, just from what we know physically is going on with the spring oscillating. So I picked the cosine function. Now, that's what x is. X, my guess is a cosine omega t. I plug that in both places I see x in this formula. So over here, real simple, I just have a cosine of omega t right there for x, and the minus k over m is here. I skipped some steps because I want to make this concise and show you the highlights and not focus on the details. But if you take the derivative of this twice, okay, then you get this. The derivative one time is negative a omega sine. Take the derivative again, you get negative sine, derivative is negative cosine, and we get an extra omega because of the chain rule. So here's the derivative. So again, I plug this in and I'm churning it out and seeing what I get. I get to this line. This is possible because if we have cosine here, we have cosine here. We can divide those out. We could divide the a, and what's left, if we eliminate the minus signs, is this. But remember, from when I just was thinking logically, using common sense in mathematics, omega is 2 pi over the period. And omega squared is 2 pi over the period squared. And so if I do some algebra, I skip the steps because I'm showing the highlights. I got to square this out, bring the t over here, bring everything else, and then take the square root of both. I get this, okay? So there's the derivation. I make a differential equation using Newton's second law. I plug in a guess. I take the derivative twice on this side. I just plug it in over here without doing anything because there's this x. Work it through, cancel out terms, and figure out what omega is. And then knowing that omega is this just from common sense and mathematics, we can figure out what the period is. That's the derivation. Okay? Well, if you have enough energy and you want to know how to derive the period of a pendulum formula, then let's go on. So this is the last thing. So this is the formula I put all the way back on page 1 of the notes about 45 minutes ago. This is how you derive it. Again, you start with Newton's second law, which is a differential equation, because the acceleration is the double derivative of position with respect to time. But here's the thing. I can't use the variable x because as this thing is oscillating, it's tracing out part of a circle. And so the symbol we use when we're tracing out a part of a circle is an arc length s. So this is like x, but along a circular path, a part of a circle, arc length. But it works the same way, the second derivative of the arc length with respect to time. Now what's the net force? So here's the pendulum at the position when I move it to the left. There are only two forces when I let this go. There's the earth pulling down constantly. It never stops. Fg is mg. But the string prevents this from falling straight down. That string actually acts like the normal force does on an inclined plane because this is going to accelerate perpendicular to the string force. Like something on a hill accelerates perpendicular to the normal force. So we can use an inclined plane analysis because at this moment, if we were to snap a picture, we do have a little inclined plane here. And remember, we're not allowed to draw components here, but there's a little triangle here. And this opposite side is what creates the acceleration. The opposite side is mg sine theta. This is the hypotenuse. Mg times the sine gives us this opposite side. So this is the forward force. Why is it minus? Because when I move it left, the force is to the right. When I move it to the right, the force is to the left. So I need that minus sign. But mg sine theta like on an inclined plane. F net. And then we divide by the mass. You see the masses go away, that gets us to here. Here's the problem. If I make an arc length formula like S equals A cosine of omega t, I could plug it in on this side. But what do I do here? I can't plug in a guess and get an answer here. So what I have to do is cheat. Yes, you heard me right. I have to cheat. Well, the fancy word we use for that is we make an approximation. Here's the oscillation, right, on a way down. So this is the actual path of the pendulum ball. The sine of this angle, if I make a right triangle like this, is opposite over hypotenuse. So I could substitute this sine theta with x over L, opposite over hypotenuse. Still, I've got a problem. I've got S over here and I've got X here. So here's the cheat. I'm going to say that this distance right here is the same as this distance. Is it really true? No. Okay. This is a little bit longer. However, if I keep this angle small, like this, the X and the S are pretty much the same distance. And this is pretty close to true. It makes like less than 0.1% error, maybe less than 0.01%. So this is why when we generate this formula, it came by getting to here and making this approximation. We can't swing the pendulum ball like this, big giant arc, because then this isn't true, this formula isn't true. Well, we could do that, but we just can't use that formula for that kind of oscillation. It only works for small oscillations. So I made that little cheat, and now I get to here. And I've got S on both sides. I could make my reasonable guess again. S equals A cosine of omega t, like I did here with X. I skipped all the steps because it's the same thing, only with G's and L's instead of K's and M's. And we get to here. Just like we canceled everything and we had omega squared was K over M, now we have omega squared is G over L, what we had here. And remembering that omega is 2 pi over the period, so omega squared, we solve for the period and we get that formula right there. Again, no amplitude and no mass in this formula. The mass dropped out over here and the amplitude is not anywhere in the formula except that this approximation. We do have to keep the amplitude reasonably small for this formula, but 1 degree, 2 degree, 3 degree, all the same period, as long as we don't go start swinging like that. So that's it, simple harmonic motion, okay? And I just want to go over what we saw in the video today. Again, we learned the kinematics behind simple harmonic motion, cosine function, but I could use the sine function, so it's trig, some kind of trig function, taking derivatives to get velocity and acceleration. We've got period formulas that you want to remember. Actually, some of these are on the reference table that you get on the AP. I think you got to look it up. And then we studied simple harmonic motion and Newton's laws, be able to draw these force diagrams, realize it's a spring force that's causing that oscillation, or you could have friction-driven simple harmonic motion, like with a shake table, shaking back and forth, or stacked blocks. And here's some analysis. So simple harmonic motion, Newton's laws. Then we studied simple harmonic motion and energy, spring energy at the end, kinetic energy in the middle, and a combination in the middle, and then our analysis. And then a little bit about energy as a function of time. But again, this is probably more important, in my opinion, in terms of getting the most best chance of getting a high AP score. Then we studied vertical spring oscillations. We could ignore the gravity and pretend that there's only spring energy at the ends, kinetic energy in the middle, and a combination of the two, just like the horizontal situation, as long as we call this a new x equals 0. And here's a calculation example. And then we derive the periods for mass on a spring and a pendulum. Okay, so that's simple harmonic motion. Hope you stayed with me, and I will see you in the next review video, gravitation.